Okay, let's start. Good morning. So this week, we're going to focus on this number, determinant. We already discussed the determinant of 2 by 2 matrices. This week, we're going to generalize it to arbitrary square matrices. But before that, I wanted to discuss this LU factorization or decomposition in more detail. I wanted to give some examples. And there isn't anything fundamentally new here. It's just that when you do row operations, when you're trying to reduce a system, if you're careful about which operations you do first, you end up with a certain factorization that seems to be useful. And it turns out also that this is, for instance, very useful in computing the determinant of a matrix, at least for large matrices. So, and this is, so I'm going to give a rather high-level description of this. We're going to do a bunch of examples, but the main idea is this, okay? Elementary row operations correspond to left multiplication by an elementary matrix. Okay, you have three types, right? You can either interchange two rows. Instead of that, you can scale a row, or you can take one row, scale it by some number, and add it to some other row. And the other thing is this. This is sort of the new, perhaps, observation, namely that I can collapse a couple of elementary row operations to be something of the same type if the corresponding matrices are from the same group. Okay? So I can group similar matrices together. So here's an example for this. Okay. Yeah. I want to start with this example. Now, the terminology around this LU type factorizations get somewhat messy. Different people call the same thing different things, and so on. So let's look at this. So let's say that my matrix A is a 3 by 4 matrix. Its entries are these: 1, minus 3, minus 4, 1, minus 3, 7, 6, 1, minus 4, 6, minus 2, 2. Okay? And as usual, let's say that I'm trying to row reduce this. Okay? Now, I haven't discussed this so far. I just said that, when you're trying to row reduce a matrix, just do whatever you want. You don't need to follow any order. But there are indeed certain algorithms that tell you what to do first. One of them is this Gaussian elimination, which says that first focus on the first column, look at the top entry, and get rid of all the entries below it. Okay? So take this first row, get rid of this number, get rid of this number, and keep going like this. Once you're done with the first column, switch to the second column, start with this entry, go down and so on. So let's try to do that. My first operation is going to be this. Take the first row and add 3 times it to the second one, and add 4 times it to the third one, so that I can get rid of this and this. So the first row is like this. Then I have here 0. So I'm multiplying by 3. Minus 2, minus 6, minus 2. Sorry, it's not minus 2. Multiplying by 3, minus 9, minus 12. So this is a 4. Okay? And then let me do the same thing here. So this is now 0, multiplying this by 4, minus 12, plus 6, minus 6, minus 16, minus 2, minus 18. 4 plus 2 is 6. Okay? So you see, now we're done with the first row, first column. This is as far as you can go. Then let's look at the same thing. I'm going to use this entry to get rid of this one. And somewhere here, let me record the operations. So E1 did what? It took the first row and added 3 times it to the second row. And it did also the following. Took 4 times the first row, added it to the third row. So now if I were to take this and get rid of this using it, I get this. So this is going to be the second operation. 1 minus 3 minus 4, 1. 0 minus 2 minus 6, 4. 0, 0. So I'm multiplying this by minus 3. Okay, maybe I should do it here. Minus 2 minus 6, 4. If I were to multiply this by minus 3, I get 6, 18, and minus 12. This I'm going to add to this. This is 0, this is 0, this is minus 6. Okay? Usual stuff. All I did really here, so there's nothing new, but I was careful as to what to use. So my second operation is this. Subtract 3 times the second row from the third row. And certainly, this is in echelon form. It's not the unique echelon form because there's no such thing. Recall, echelon forms are not unique, but certainly it is in echelon form. And it turns out that in the context of LU factorizations, this is what people are most interested in. Not really the reduced echelon form, but for them, some echelon form is good enough. Okay? So now let's write out the matrices. So we can think of it like this. In both E1 and E2, I took one row and added it, some multiple of it, to a row underneath it. Which means that when I look at the matrices that correspond to these two guys, both of them are going to be so-called lower triangular with ones on the diagonal. Okay? So E1 is going to be like this. And then I have 3 numbers. Row 2 plus 3 times row 1. So here I have a 3. And row 3 is row 3 plus 4, row 1. So this is 4, this is 0. Okay? So this is what is called a, this has a couple different names. You can call it lower triangular, right? Because it has only entries on the diagonal and below it. And above the diagonal, you don't have any entries. Lower triangular with ones on the diagonal, you can say. Some people call this a unitriangular matrix. Uni meaning referring to diagonals being 1. Some people call it unipotent or lower unipotent. This has a bunch of different names. Let me just write a couple of them. With ones on the diagonal, aka unitriangular, lower unitriangular. Aka lower unipotent. Its power is 1. It's something like that. So, and I can do the same thing with E2. And this too is of the same type, okay? And row 3 is replaced by row 3 minus 3, row 2. Maybe I should draw things here. Okay. These three numbers, in the context of lower unipotent matrices, these three numbers really determine the whole matrix in here too. So it allows you to compress the data, in a sense. Okay. Any questions about this so far? This should be, you should be familiar and comfortable with this so far. Okay. So now, when we're talking about factorizations, what I want to write is something like this. A equals a bunch of matrices multiplied together. Okay? And let me call this matrix A sub R. A, so it's an echelon form for A. An echelon form. So in matrix notation, then I can write it like so. Left multiplication, which means that first I'm multiplying by E1 and then by E2, and then I get A sub R at the end. Now I can send these two to the other side so that I can have, I solve for A, right? A equals something. And since you're going this way, first you need to send this to the other side. So that first you're going to see E2 inverse, and then you're going to see E1 inverse. Okay? Now, what are these matrices? We had discussed this a little bit. But by a group here, I mean, this is also part of what I mean. I'm going to write down the definition in a second. I want my matrices in my group to be so that their inverses are also of the same type. And indeed, the inverse of this is of the same type. It is also a lower unipotent, and likewise for this. Recall that the rule for this was you just put minuses here. And likewise here. Okay. And so now, writing this out, I get this. So 1, 0, 0, minus 3, 1, 0, minus 4, 0, 1, and then that. 1, 0, 0, 0, 1, 0, 0, 3, 1. And let me leave this A sub R as is for now, because I want to first multiply this to get one lower unipotent matrix. Okay? That I want to group matrices of the same type, essentially. And so when I do this multiplication, I'm again going to get a triangular matrix like this. And the entries are going to be this. So this is minus 3. And then this is minus 4. And then this is 3. And let me open up this A sub R as well. 1, minus 3, minus 4, 1, 0, minus 2, minus 6, 4, 0, 0, 0, minus 6. Now note that finally we have an L for lower now, and we have a U for upper. This is not quite upper triangular because it's not a square matrix, but it's an echelon form. It's the best you can get in this case. Okay? Any questions about this? Recall, so last week we sort of did a similar thing. This is, I'm thinking of it like this, okay? These two matrices are, I can think of them as transformations. And I'm thinking of this as the front end, and this is sort of like the back end. This is an invertible matrix, okay? So this isn't quite telling me anything about, rank and nullity, but if I were to look at this, it does tell me the rank and nullity of the matrix, for instance. So this is the backside of what is happening. That's one. Another thing is this. When you're trying to solve a system, so this is one of the uses of this. So one use of such factorizations. Apart from, the factorization telling you how the matrix is operating. This is sort of like the back end, and this is the front end, and this is really how this matrix is operating. That's one. The other use of this kind of a thing is this. In applications, typically, this matrix A, this transformation matrix, or the matrix of coefficients, come from your system. Okay? You have a system, and this matrix is what your system is telling you to do, essentially. But, and you want to solve for, so your system gives A, let's say. But also, you have many outputs. Let's say B1, B2, B3, and so on. Okay? And you want to solve all these equations. Okay? Want to solve AX equals B1, let me say AX1, AX2 equals B2, and so on. Now you can solve this system. We learned this by now. And then you can go to this system and solve it again. And then to this system and solve it again, and so on. It turns out that solving such a system has cubic cost. Okay, let me just leave it like that. So let's say that you want to perhaps invert the matrix or whatever you want to do. It doesn't matter, because at the end of the day, in order to multiply two matrices, let's say two square matrices, you end up needing to use, in the case of 3 by 3, typically you end up needing to use 27 operations every single time. Multiplications. I'm not even counting the additions. So each one of these gives you cubic cost. Instead of doing that, you factorize your matrix into L and U. This too has cubic cost. But then once you have this factorization, solving the system, each of these systems becomes quadratic.
So this is like the same cost up front, but it saves you time.
Essentially, yes. Yes. So maybe I should write it like this. Solving each system equation has cubic cost. This means that if my matrix is n by n, or if I have n unknowns, its cost, the cost of finding those n numbers are going to be n cubed. And for each of these systems, for each of these outputs, you're going to have an additional n cubed. LU factorization is also cubic, in cost. Exactly. In cost. But once you have it, solving each of these systems have a quadratic cost. Each equation has quadratic cost. Okay? So let me do a comparison. Let's say that you have n unknowns and you were given p outputs. Okay? And p outputs. If you use this method without the factorization, so solving each equation requires approximately, this is not exact, but it requires approximately p times n cubed multiplications, number multiplications. If you use vanilla matrix multiplication. Instead, if you do LU and then solve each of these systems using this LU factorization, the cost ends up being n cubed plus p minus 1, or rather p n squared. First LU, then solve, requires n cubed plus p n squared multiplications, number multiplications. Okay, so cubic. So this is like your cost. You don't want this to grow as fast. This is much better than this.
Okay. So is n like the dimension of x, and then p is the number of equations?
Yes. Exactly. Yeah. I should say number of systems of equations. Yeah. Okay. This is a beautiful topic, but it turns into something called algebraic complexity theory. There are people who look at algorithms and they will look at if things can be done more efficiently and so on. Unfortunately, it seems to me that this is too advanced for this class, so I don't want to discuss this too much in detail, but this is sort of like one of the reasons. If you're interested in this, we can perhaps discuss it later. But, okay. Did this sort of like satisfy?
Okay, that totally makes sense.
Okay, okay.
We learned about big O analysis and
Okay, good.
But it's like, hey, this is like this one is slow and this one is fast. In fact, people say so just do that one.
Okay. So that's that. Any other questions about this? So for instance, here's an alternative to this. I can certainly go a little bit further and say, okay, let me also normalize the pivot entries, okay? That you can do by taking out a diagonal matrix, okay? So now the same example, I'm going to look at example 2, E1, E2, and then I'm not stopping here. For E3, I'm going to do this. Let me erase this. I'm not going to use, so at this stage, I can't use a lower triangular matrix. The do things, so simplify things even further, but I can scale the second row and the third row, okay? And let me call this E3. So now I have 1 minus 3 minus plus 1, 0, 1, 3 minus 2, 0, 0, 0, 1. Okay? So E3 does the following. Replace the second row by minus 1 over 2 times row 2. And replace row 3 by minus 1 over 6 times row 3. You see, when I look at the matrix for E3, it is not quite of the same type. This is a different group, okay? I'm going to think of it as a different group. And recall that we called such matrices diagonal. And of course, its inverse is also diagonal. And it's simply this. Okay? Now, updating this calculation over here, I have something else. Let me call this E3. And now I'm calling this new echelon form, A sub r. And now this is true. And you see, this time E3 is closest, or rather its inverse is closest to the end result. And then E2 inverse, and then E1 inverse. We already computed this. It is this product. Let me erase it. 1, 0, 0, minus 3, 1, 0, minus 4, 3, 1. And then I have 1, minus 2, minus 6. And then that matrix over there. Um, 1 minus 3 minus 4, 1, 0, 1, 3 minus 2, 0, 0, 0, 1. Okay? So this is yet another factorization. People call, for instance, the first example an LU factorization. The second example, LDU factorization. Okay, because it's diagonal. It says D, L, lower unipotent, and this is echelon. Maybe I should write it like this. Okay? And so you see, so from this perspective, this is not really that useful, but I still do think that this is somewhat illuminating, because now I can think of these two as front end, and this as the back end. Okay? So you see, this is a scaling matrix. Doesn't do anything in the first coordinate, scales by minus 2 in the second coordinate, and so on, and it says shear. Okay? Just like we looked at, so just like the situation for 2 by 2 matrices, that is to say, linear transformations of the plane, you sort of like factor out scaling operators, or scaling transformations, shear transformations, and of course there's a third one, which is the rotations. Turns out that in this case, what is more important, what is more in use is what is called a permutation matrix. And this is a generalization of row swaps. Okay? So let me be more explicit about these examples of groups that I'm also mentioning at the same time. So one example we have is lower unipotent matrices, E1 and E2. The other example we have is diagonal matrices. So examples of matrix groups. Lower unipotent. Of course, the same thing holds for upper unipotent as well. I can think of upper triangular matrices. In this case, I didn't use them, but I could if I wanted. And diagonal matrices is another group. It's another matrix group. So now let me adjust my initial matrix A, okay? Because in this case, things turned out to be nice. But let's say that I don't really want to sort of start with the first row and use this first entry to get rid of these two and so on. One reason you might not want to do this, or you might want to sort of get rid of some other rows, is because perhaps this one is somewhere here. Okay? So think of this example. I'm just going to permute the initial rows of A, and we're going to start with this. So this is example 3. Okay. Now, if you wanted, again, an LU decomposition here, you would say, OK, I'm going to first take this, because you see, you cannot go up. All you can do is you can go down. And I'm going to scale it by minus 1/4, so that I have a 1 here, and then add 3 times it to this one and so on, to get rid of this entry and this entry. You might try doing this, and it would work. It would give you a different decomposition. Or you can do this. You can say, I'm going to take the third row and add 3 times it to the second one, 4 times it to the first one. Okay? This time, since I'm going up, it's going to be upper triangular. And of course, the calculations are the same. Let me not spend a lot of time with those. 0, minus 2, minus 6, 4, 0, minus 6, minus 18, 6. That's 1. And then, likewise, I can take this and get rid of this, for instance. Minus 3, minus 4, 1, minus 2, minus 6, 4, 0, 0, minus 6. Okay. So now this time, E1 and E2 are upper triangular. I took a row in the third, so I took the third row, and I used it to clear upwards. Okay. So right? So take the third row, add 4 times it to the first one. Okay? Like this. And again, I'm taking the third row, adding 3 times it to this to get rid of this 0. And E2 is going to be something similar again. I'm taking this and subtracting 3 times it from the first one. So it should be like this. Okay. Now you see upper triangular matrices I mentioned here, like lower triangular matrices, form a group. And so I can say, this matrix equals A times, from the left, E1, from the left, E2. And then I can, if I wanted, I could have done a permutation here. Let me call this E3 this time to get this. And of course, E3 is the matrix that interchanges the first and the third rows. Okay. And so now recall that this is, again, an echelon form. Maybe I should just call it U. And I have, indeed, this. Okay, sending everything to the other side, I have this now. Now these two, the first and the second one, are inverses of upper triangular matrices with ones on the diagonal, which means that the inverses too are going to be of the same form, and their product too is going to be of the same form. So this is upper unipotent. This is echelon, and this is what is called a permutation matrix. Okay, so it's a swapping matrix. So calling these two, if you want, let's call it V, and this P, now you have something called a VPU decomposition or factorization. It turns out that this is not very popular. And what people like doing is to leave the permutation, or rather, do the permutation first. Okay? Instead, it is more popular to use A equals P L U. It turns out that there is indeed a way to do this. And if you do the permutation first, right, because if it's in the left, that means that I use the permutation first. Then instead of using uppers, you can do lowers. And this is what's called the permuted LU factorization. Okay. The point is that you can't quite do LU factorization for any matrix whatsoever. For instance, in this case, you wouldn't be able to do this. But if you permute the rows, then you can do it. And that's why it's called the permuted LU factorization. Any questions about this?
What's VPU?
So V is the upper triangular matrix with ones on the diagonal. That is the product of these two. I didn't write it down, but it is that. And P is this inverse matrix. In this case, the inverse of E3 is, of course, itself, right? Because if you're interchanging 1 and 3, the inverse of it is interchanging 1 and 3.
What's V for?
I didn't want to write U. It's still upper triangular.
Oh, it's a U.
This is a U, this is a V.
It is a V, but you just changed the notation so that we can have double U's.
So U prime.
So V stands for what?
It doesn't stand for anything.
Oh, I see.
It's the letter after U. Okay. So now you can imagine how you have all these different factorizations. And it has computational benefits. It also has conceptual benefits. Though it turns out that for the purposes of specifically invertible matrices, let's say that you're trying to row reduce a square matrix, this factorization is not fine enough, let's say. You need some more information about invertible matrices. And later on, we're going to discuss more sophisticated factorizations, like the spectral decomposition or the singular value decomposition. These are more important, possibly, factorizations. But for the purposes of solving systems efficiently, this LU factorization or its variants are the most useful ones. And most, at the very least, they're the sort of starting point. I should also mention what a permutation matrix is. Let me give a definition of a permutation matrix. And just like the lower triangular matrices or the diagonal matrices or upper triangular matrices, permutations too end up becoming a matrix group.
Is the L in the PLU, is that the same thing as like the V or the U prime?
No. So I'm telling you that so this P is going to be the same as this P, but L here is lower triangular.
Oh, okay.
Yeah.
So it's the same thing if we like did it on the other example too?
Yeah, yeah. So the idea here is, so the difference between this and that is the following. Once I do row reduction somehow, and once I figure out this form, I know that at this stage, oh, you know, the rows of my original matrix are scrambled. The third row should really be at the top, the second row should be at the second row, and the third row should be at the third. The first row here that we started with should be really at the third row. So what you do is, instead of starting like this, you sort of permute the rows before doing any row reduction, essentially. And that's how you can get this P at the end.
In general, like permuting a upper triangular to a lower triangular is the same as this?
Yeah.
Okay.
Yeah.
You can flip them and it works the same.
Yes.
From upper to lower, it's the same.
Yes. It is slightly more complicated than that. There are situations where you can permute a lower and it's going to give you a lower. But in this case, it turns out to be like this. Yeah. There are certain technical matters that I don't really want to get into because we're not sort of like looking into row reduction in this detail, or at least in this class. But certainly if you were to take a more advanced class like a numerical linear algebra or algorithms or something like that, I'm sure they would go into all these things. In reality, when you're trying to use a computer to do these row reductions, even though from an abstract point of view you can just do whatever you want, it turns out that at each step there's a most reasonable choice as to which row to use to simplify which other rows. And so these are called partial pivoting and so on. There's a bunch of methods and algorithms that are more sophisticated than anything that we've discussed, but some of the things that we've discussed. But I think at this stage, something around this is like this much is enough. Okay, yeah. Any other questions? So for instance, another thing that I find personally very interesting is this, that typically in class, you're going to realize most of the matrices that we looked at had integer entries. And then when you're doing row reduction, eventually you sort of like start seeing rational numbers. But there's also a way to never use rational numbers, so ratios, keep to integers, so only ints. Things get slightly more complicated there, but still it can be done. I find those things very interesting as well. If you want to sort of challenge yourself, you can think of taking some matrix and trying to row reduce it without seeing any ratios along the way. That's an interesting, fun exercise. There's lots of different variations behind all this stuff. Okay, what is a permutation matrix? Its definition is rather straightforward. A permutation matrix is a square matrix such that in each row of it and each column of it, there's exactly 1, 1, and all other entries are 0. Is a square matrix P such that on each row and on each column, I guess if you have one, you have the other one as well, but let's write it out. On each column, exactly one entry is 1, and all other entries are 0. Okay? Let me immediately record that indeed permutation matrices too constitute a group. I still haven't given you the definition of what it means for things to be a group, but perhaps I can mention it tomorrow. So is also a matrix group. Let's write down examples. So here's the question. How many permutation matrices are there if you're looking at n by n matrices? Because this is a very strict condition that we're using. Yeah. I mean, maybe it's the other way around. So, example. When n is 1, of course, 1 by 1 matrices. So if in each row there's going to be only 1, 1, that means that I only have this 1 by 1 matrix. In 2, I have 2. Okay? Either it's the identity or it's the matrix that corresponds to swapping or reflecting, depending on how you're thinking of it. In 3, I'm going to have 3 factorial many permutation matrices. So that is to say, I'm going to have 6 matrices. Identity. So you can think of this as the permutation that doesn't do anything. In math, it turns out that it's a good idea to keep track of the thing that doesn't do anything also. Or I can have this. I'm swapping the first and second. I can swap the first and third. I can swap the second and third. Or I can swap all three of them. 1 can go to 3, so let me write it like this. 1 goes to 3. Like this, or it can happen like this. So 2 goes to 1. There's a third one. My brain stopped, so I'm not going to write it, and we're out of time. And tomorrow, I'll tell you which one it is. Okay? These permutation matrices are very important. It's part of this whole thing. Thank you. I'll see you tomorrow. Okay, I think we should start. Good morning. So today, we're going to discuss more rigorously this definition, an axiomatic definition of a matrix group. Recall that yesterday we were using this idea of a group in the context of LU factorization. I said, oh, you have a bunch of matrices and you want them to be of the same group so that you can collapse them together and have a nice decomposition. And here's a definition. Okay? It's just that I'm going to call a subset of matrices, and they have to be invertible, a matrix group, or just group, if the set is closed under matrix multiplication and matrix inversion. Okay? It's that simple. And yesterday we saw a couple of examples, and let me reiterate this idea here. Upper triangulars, so upper unipotents, lower unipotent matrices, diagonals, right? So for instance, here I'm literally saying, or I guess I'm trying to say that if I were to take two diagonal matrices that are invertible, certainly their product would also be diagonal, and the inverse of a diagonal matrix would be invertible also. So saying that diagonal matrices is a matrix group is code for that. Another example, which I want to spend some more time today on, is permutation matrices. Another example is rotation matrices in 2 dimensions, for instance, in I believe problem set 3, there was this problem about 2-dimensional rotations and how rotating 2 matrices, or multiplying 2 rotation matrices gives you another rotation matrix. You were really verifying there that rotation matrices constitute a matrix group. Here's another important class that's going to show up later on. Orthogonal matrices. Okay, this is a generalization of a rotation, if you want. And instead of giving you the formula for something like a rotation, you're instead given an equation, okay? And by definition, a square matrix is orthogonal if its inverse is its transpose. if A inverse equals A to the t. So these are a certain class of matrices that is easy to invert, right? So inverting matrices typically is not that easy. Takes certain steps. But if your matrix is orthogonal, inverting is just all you need to do to invert is to take the transpose. Another way people write this is that they send this to the other side and they write it like this: AT A equals I equals A AT. Okay? Now, of course, a rotation matrix is an orthogonal matrix. Is an orthogonal matrix. Let's verify this. So let me take R theta, okay? So recall that this is the 2 by 2 matrix. So let's just focus on 2 by 2. This is the matrix with entries cosine of theta minus sine of theta, sine of theta, cosine of theta. Well, let's look at the inverse. Recall that we had this formula to compute the inverses of matrices rather straightforwardly. And all you need to do is put here the determinant. Determinant here is cosine times cosine minus minus, which is plus sine times sine. So cosine squared plus sine squared is just 1. And then I flip these two, so they have to stay the same. And then I put minuses in front of these. So this is now sine, this is minus sine. Of course, this is nothing but the transpose of R theta. Okay? So indeed, rotation matrices are orthogonal, or in other words, orthogonal matrices, this notion of orthogonality is a generalization of a rotation. Okay? Any questions about this? Yes?
Would you say that orthogonal matrices are a generalization of rotation matrices? Are you saying that all orthogonal matrices are rotation matrices, or are you saying that generally rotation matrices are orthogonal?
The second one.
Okay.
Yes. Because here's the other thing, for instance. Permutation matrices too are orthogonal. Okay, so let's again look at 2 by 2. In 2 by 2, I have only two permutation matrices, 1, 0, 0, 1, identity, or 0, 1, 1, 0. This is the matrix that reflects the plane along the main diagonal y equals x. And this is the matrix that doesn't do anything. Certainly, this is orthogonal. Right, so its inverse is itself, of course. And the transpose of this is the same thing, because it's a symmetric matrix. We're going to learn that terminology as well, but let's leave it at that. So what is the inverse of this? Well, its inverse is itself, you see. Because if this transformation reflects along y equals x, its inverse does the same thing. Which, of course, is the same thing as a transpose, because this matrix 2 is symmetric. But then we had discussed this. This matrix is not a rotation matrix. Okay? So there's no theta for which r theta equals this. Right? Because by definition, a rotation matrix should be so that this entry is minus this entry. But here, this entry is the same thing as this entry. Okay? So all rotation matrices are orthogonal. Not all orthogonal matrices are rotations. Okay. Any other questions about this?
So would the easiest way to check if something is orthogonal would just be to like take the transpose and then multiply them together?
Yeah. Another example is minus identity, for instance, is orthogonal. Right? Because minus identity is minus 1, 0, 0, minus 1. Again, this is symmetric. Right? So that means that if I were to take the transpose, I would get the same thing. Nothing changes. And its inverse is itself. Okay? And really, people so let me say it this way. Even though it is not the case that all orthogonal matrices are rotation matrices, that statement is almost true. Okay? So any orthogonal matrix in 2 dimension, for instance, this is a nice exercise, is either this, so it's of this form, or it is that times this. Okay? So this is a nice exercise. Let me write it. It's for you. Find all 2 by 2 orthogonal matrices. Okay, so for this, what you need to do is to say, okay, so I have A, B, C, D. Let's say that I start with this, and when I transpose it and multiply, so A, C, B, D, I want to get identity. Now, this gives you 4 nonlinear equations in A, B, C, D, but still, this is a system that can be solvable, that can be solved. Solve for A, B, C, D. Okay, this is a very nice exercise. Okay. So that's this notion of groups. So this notion of groups is important in the context of something like LU decomposition. It really allows you to sort of put things together and lump matrices together without changing their type, so to speak. But at the same time, it turns out that this notion of a group is much more general. And using this idea of a matrix group, you can represent an abstract group as a matrix or as matrices. And so that is sort of what is a starting point of what is called representation theory. It is very important in physics and chemistry in many different fields. Somehow, all around science, people were able to see certain relations and interpret them as matrices, and that sort of opens up this whole field, and it allows them to use linear algebra, even though the problem doesn't seem that linear algebraic to at first glance. So this is an important concept. So let's go back to permutation matrices. Does any of you remember the definition I gave yesterday?
Is it like there's a single one in each row and each column?
Yeah. Yeah, so it's a square matrix. With exactly one on each row. Okay? This is the definition in n dimension. In 2 dimensions, like I mentioned over here, I have only 2 permutation matrices. And I was writing last time the case for 3 by 3, and that's I forgot one of them, couldn't remember it. Let's write it. If n is 3, I have 6 permutation matrices. You have to start with the identity. Okay. 1. Okay. So why do I call this? So this is the identity, of course. It's the identity matrix. It's a permutation that doesn't do anything. So I have 3 channels, right? These are the inputs. X, Y, Z. X is sent to X. Y is sent to Y. Z is sent to Z. So this permutation is the permutation that doesn't do anything. But then I can start shuffling the channels. So for instance, I can look at matrices, permutation matrices, that shuffle only 2 channels and keeps the 3rd one fixed. I can either fix the 3rd one, or the 2nd one, or the 1st one. And that gives me 3 more permutation matrices. Yeah. Okay? So you see now, this matrix is taking the 2nd entry to the 1st entry, and then the 1st entry to the 2nd entry. Doesn't do anything with the 3rd entry. And then I have, so 0, 0, 1, 0, 1, 0, 1, 0, 0. Now this matrix doesn't do anything with the 2nd entry, keeps the 2nd channel fixed, but shuffles the 1st and the 3rd channels. And then I have one final in this shape. And this permutation matrix fixes the 1st entry and shuffles the 2nd and 3rd entries. Okay? And if you wanted, you could also think of this using this block matrix notation. And this is an important idea here. Okay? So here the block is hard to see, but the block looks like this. Okay? I spread out the block, if you want. And here it looks like this. So somehow what I really did here is that I took that 2-dimensional permutation matrix that flips the channels, and I put it in different positions in a 3 by 3 matrix. Okay? And I have 2 final ones, and these 2 shuffle all 3 channels together. Okay? So 1 goes to 2, 2 goes to 3, 3 goes to 1. This is 1, for instance. What this matrix does is that it takes the 1st entry, turns it into the 2nd entry. It takes the 2nd entry, turns it into the 3rd entry, takes the 3rd entry, turns it into the 1st entry. And then I have another one, which does this. So 1 to 3. 3 to 2. No. 1 to 3. 2 to 3. 3 to 1. 1, 3. 3. Oh, yeah. but I wrote it here.
1 to 2, 2 to 3, 2 to 1.
1 to 3, 3 to 2.
Wouldn't 3 to 2 be in the third column?
Oh, yes. Thank you. Okay. Okay, now it works. Okay, yes. 1, the first channel goes to the third. The third channel goes to the second. Second channel goes to the first. Okay. Now it works. Okay? Any questions as to how I interpret these matrices this way?
I'm assuming 1 to 2 and 2 to 1 are the same matrix, the resulting one. Like
Yeah, exactly, yes. So this switches, for instance, 1 to 2 and 2 to 1. Yeah. Now, this notation kind of gets confusing, I think. Or rather, it is of course useful to think of permutations as matrices. It allows you to do row reduction, for instance, and use them in the context of LU decomposition. But there are other ways to represent this. And so let me actually redraw all these this way and put different visualizations, okay, certain visualizations. So I'm going to write these here. This is one type. Another type are these three that shuffle only 2 channels. Second one, and then the third one is this. And then we have the final class, which shuffles all 3 channels. That's one. And then there's the other one. So here's one way to visualize this. I can think of the inputs and the outputs as terminals. Okay, so I'm going to write it like so. So I have the x, y, z input terminals and x, y, z output terminals. Or maybe say u, v, w output terminals. And because this matrix is not changing anything, I think it's better to say x, y, z still. X, y, z. I'm going to think of this matrix as 3 wires like this. Okay? Doing the same thing here, x, y, z, x, y, z gives me this. You see now y goes to x goes to y, z is kept as is. So now you have a crossing of the channels. And if I were to do the same thing here, the middle channel would be fixed, the other 2 would be interchanged. And here the first channel is mixed, and first channel is fixed, and the other 2 are mixed. Okay? Doing the same thing here, I have again 3 channels. 1 goes to 2. Okay, so I have 3 channels. 1 goes to 2, 2 goes to 3, 3 goes to 1. 1 goes to 3, 3 goes to 2, 2 goes to 1. Okay? So you can think of these matrices as these shapes as well. And further, multiplying two permutation matrices correspond to attaching these wire connections, let's say, these terminals together, these ports together. So for instance, I can do this. Let's, for instance, take the first two matrices and multiply them. I told you that permutation matrices constitute a group, and I know that because of that, the end result is going to be a matrix. So let's just compute it. So let me take 0, 1, 0, 1, 0, 0, 0, 0, 1. And then I'm going to take the second one. 0, 0, 1, 0, 1, 0, 1, 0, 0. Okay? So now let's multiply this. 0, 1, 0, 0, 0, 1, 1, 0, 0. So you see we got this one. Okay? Now let me compare the wire symbols, let's say. So the wire symbol of this is this. 1 goes to 3, 3 goes to 2, 2 goes to 1. Okay? This looks like this. 1 goes to 2, 2 goes to 1. 3 is kept. Here 2 is kept, and 1 and 3 are switched. Now I might mess this up, but the idea is that if you were to put these two on top of each other in the correct way, you're going to get this shape. Okay, let's try this out. So let me say, perhaps, I think I should start with this. Okay, so I have 3 terminals, go back to 3 terminals, and then I'm going to have another 3 terminals here. So here I use this, and then I'm using this one. Okay, this is correct. Now you need to tidy things up. If you start here, you end up at the third. Okay? If you start at the second, you end up at the first, and if you start at the third, you end up at the second. Okay? So matrix multiplication corresponds to putting the associated wire symbols on top of each other. And if you follow things, it gives you the correct matrix. So you can do matrix multiplication, or you can multiply this way. Doesn't matter. So that means that put the wire symbol, let's say, of the right one on top. Okay? Because I'm imagining that the signal is coming from the top and like it's going downwards. Some people think the other way around, in which case you would need to switch the orders. Okay? Any questions about this? And another thing I'm going to introduce here. To denote each of these 3 classes, I'm going to start using tetrominos. Okay? So this class is, it consists of only one matrix, of course. It's the identity matrix. And I'm going to use this. This has 3 towers. Think of it this way. Each of these boxes is one separate tower. And because you don't have any height, I'm telling you, don't mix anyone. Here, I'm going to represent these matrices like this tetromino. Okay? This tells me fix one of the channels and mix up the other 2. Which other 2? It depends. Okay? So you have to write everything down. And here, you're mixing all 3 of them. And so I'm going to use this tetromino. Okay? Any questions about this?
So you don't like, the only information that tetrominoes give you is like what class you're in?
Yeah, the type, yeah.
It also gives you the dimension, doesn't it? Like if you only have the tetromino, you also know the dimension of the permutation. Because like if there's 3 boxes.
Exactly, yeah, yeah. The number of boxes add up to the dimension, yes, that's true. Yeah. Exactly. So if I had, oh, let's do it here as well. So in the case of 2 by 2, I can only use 2 boxes. And either it's going to be this way, or it's going to be this way. It just happens to be the case that in the case of 2 by 2 matrices, each of these classes consists of 1 matrix. Here there are more, and you can imagine how if you had a 4 by 4, if you were looking at 4 by 4 permutations, things would be slightly more complicated.
Does that mean if so this grows, like you get more tetrominoes like the same way as partitions grow?
Yeah. Yeah, so this is this idea of a partition if you want. So for instance, I'm saying I have 3 things and I'm partitioning them into 2 plus 1. That's because I'm mixing 2 channels and one of them I'm leaving as is. So this is another terminology that is also very useful whenever you're trying to handle symmetries. But so far I think this much is enough for us. Now I'm going to add one more piece of information, okay? Recall that we had discussed how in 2 dimensions we really look into, so like when we're talking about rotations, the traditional thing is to go counterclockwise. But mathematically speaking, there is no difference really between counterclockwise and clockwise, in the sense that you could do the formalism for clockwise matrices and everything would work out fine. What turns out to be important is that there are only 2, okay? In the plane, it's obvious. You can either rotate this way or this way. But it turns out that in any dimension, this is the case. And so this is this notion of chirality or orientability. Okay? And so here's a psychological statement that I think is illuminating. I'm still looking at 3 by 3 permutation matrices. Okay? Now, if I say this is a coordinate system for 3 dimensions, and if I tell you to imagine, typically, you imagine this as if this is like a 3-dimensional thing, and you're looking down, okay? So you're like this, and you're looking down. But really, there's another way of seeing the same picture in 3 dimensions. You can also think of it as you're looking up, okay? Can you see this? Right, so you can interpret this 2-dimensional picture as a 3-dimensional thing in 2 different ways. And so this is telling you that there is either a plus orientation or a minus orientation. If I were to name these axes, the interpretation that this picture is, so in 3 dimensions, it's a 3-dimensional space that you're looking down to from this side, corresponds to what is called the positive orientation or the right-hand side orientation. So, looking down corresponds to positive orientation. And in other words, this is also the so-called right-hand rule orientation, right-hand orientation. Right-hand rule. And the idea behind this is that you point your, so you take your right hand, you point your fingers toward x, and your palm is toward y. When you roll your hand like this, your thumb points in the z direction. Okay? But if you were to imagine that you're looking up to see this, then you have a different orientation, and that is called the negative orientation. And that corresponds to the left-hand rule. Okay? Which tells you that this time, if you're imagining this to be somewhere up there, okay, sorry, I did this earlier. I'm getting confused. It is correct. I think this is correct. But if you can get this other perspective, if you put likewise your left hand in such a way that your forefingers are looking this way and your palm is that way, when you rotate, you get z. Okay. Depending on these two orientations and how these matrices switch between the two orientations, you call this either of positive sign or a negative sign. Okay? So in this context, this doesn't change anything. So certainly this should be a plus. This changes things. Okay? XYZ becomes YZX. So this is a minus, minus, minus. And then all three of these turn out to be, all two of these turn out to be pluses. So these are called the signatures of permutations. They are also the determinants of permutation matrices. So by plus I mean, of course, plus 1 or minus 1. Okay? So determinant could be plus or minus. Interpreting this plus or minus business when you're trying to compute a determinant, let's say in 2 by 2, as something about this orientation, we can go one step further and really interpret the determinant as a geometric object. Okay? And to build this geometric intuition, let's again focus on 2 by 2. Okay? And of course, we already discussed this before. If A, 2 by 2 matrix, has entries A, B, C, D, then its determinant, we can write it like this. Or it is also very common to just rewrite the matrix itself and put bars instead of parentheses, is just this, AD minus BC. Okay? Before I go any further, let me also write here. You see, this should be a plus. Doesn't change the clockwise or counterclockwise. This changes it. Okay? And certainly its determinant is minus 1 according to that formula. So now, what I want to do is to interpret this number geometrically. Okay? So here's one way to do this. First of all, I want to think of the columns. So I'm going to draw a picture. If I were to start with the unit square, so as usual, I have my horizontal vector, which is 1, 0, and the vertical vector, which is 0, 1. Well, the first column of A, AC, really is where A takes this blue vector to. And likewise, the second column is where A takes this red vector. So this is 0, 1, this is 1, 0. I'm just going to draw a caricature. I don't exactly know what these numbers are, of course, but I can imagine them to be something like this. Okay? Let's say that this is the image of 1, 0. That is to say, it's AC. And I have another one here, which is the image of this. Let me complete this into a parallelogram. Okay? So how did I do this? I took this particular vector, for instance, and I added it to the endpoint of the other one. Or I could have done it the other way around. I could have started with this blue vector, and I could have added the red vector on top of the other one. And I know that either way, I should end up at the same point. And maybe I should ask this. What are the coordinates of this point in terms of A, B, C, D? Exactly, right? Because so if the x-coordinate of this, right, is A, so you moved A units rightwards for blue. But then you also move B units for red. So if you adjoin the arrows on top of each other, then you should add the vectors. So this is A plus B, and then C plus D. This particular point. So this point is AC, and this point is BD. Now my claim is that the area of this particular parallelogram is equal to this number. Okay? Now, area it's a positive number, of course, where it's a zero number, it's 0 or positive. When it's negative, because this expression can turn out to be negative, for instance, in this case, I'm interpreting it in the context of chirality. I change the chirality of the system. Okay? Instead of going clockwise, now I'm going counterclockwise. So, better to say that the determinant of a matrix is the signed area of the parallelogram, that is the image of the unit square under A. So let me write this down. We're going to do this derivation tomorrow, but I want to write it here. So let me do this. Here. determinant of A, 2 by 2, is the signed, so plus or minus, area of the parallelogram that is the image of the unit square of the unit square so let me just leave it like that, under A. Okay? So this is the main geometric observation. It turns out that the same thing holds for determinants of arbitrary large square matrices, but then you need to use volume or hypervolume and so on. Okay? We're going to do this derivation tomorrow, but I have a couple minutes. Are there any questions about this? Okay, let me just mention then that one way to derive this is to complete this to a rectangle. It's easy to compute the area of the rectangle and then take away the extra pieces. Okay, we're going to do this tomorrow and really compute that this number just pops up geometrically. Okay, thank you. I'll see you tomorrow. Okay, let's start. Good morning. So I wanted to make a correction. I said something, I think, egregiously wrong yesterday. I said, I think I insinuated that minus identity isn't a rotation. Certainly it is. It is rotation by pi degrees, 180 degrees. Just wanted to mention that. I also wanted to mention that on Canvas I've uploaded a handout for LU decompositions. I went more into detail. So if you want to I wrote a couple examples as well, rather explicitly. So if you're interested in those kind of things, I think it might be good to have a look at it. So today we're going to focus on, again, determinants. And the first thing I want to do is to justify that this idea that the determinant of a 2 by 2 matrix has to do with area. Recall that determinant of A is AD minus BC. It's this particular number. And what I said yesterday was that if I were to take the unit square, right, so the square determined by the origin and 1, 0, the horizontal vector of unit length, and 0, 1, so that this has area 1. Then, and if I were to use A to transform it to something else, it's going to be a parallelogram. So this blue vector is going to go somewhere, and the red one is going to go somewhere else. And I can again complete it to a parallelogram. The area of this, the signed area of this, is going to be exactly this particular number. Okay? So I want to compute the area of this. So what I'm going to do is this. Instead, I'm going to compute the area of a larger region, and then I'm going to subtract the areas of parts that I've computed, that I've counted extra. So think of it like this. Okay, let me partition this even further. Okay. So the line of attack here is to compute the area of the whole rectangle and then subtract the areas of these triangles and subtract the areas of these rectangles. Eventually, I should end up with the determinants. Okay. So first of all, note that the coordinates of this particular point is, well, the first column of A. So AC. A is the x coordinate, y is the C is the y coordinate. So I can say that this length is A, and this length is C. Okay? Similarly, I can say that because this point came from this point, its coordinates are b and d. That is to say, its x coordinate is b, so this length is b, and this length, the height, is d. Okay? And finally, note that the coordinates of this point are a plus c, a plus b, comma, c plus d, because I obtained this point by adding this particular vector to this particular vector. So that means that this whole length is a plus b, which means that this has to be b. And likewise, because this is a plus b, this has to be a. And doing the same thing with the heights, I can say that this length is d and this length is c. So now I have everything I need. Okay? Let me put numbers on each of these ranges. So let's say this is 1, 2, 3, 4, 5, 6. Okay? So I can say that the area of the parallelogram equals total area minus, well, 1 to 6. So I need to compute all of these numbers. Well, the total area of this rectangle is certainly a plus b times c plus d. So now I need to subtract things. For instance, note that 1 has area b times c because it's a rectangle, and so is 6. Its area is b times c. It doesn't look like it, but it is. So I have 2 times b times c. What else do I have? Well, note that this triangle has it's a right triangle. One side has length a, the other side has length c. And this triangle too has the same configurations, has the same measurements, a against c. So 2 and 5 have the same area, which is ac divided by 2, but I have 2 of them. So minus AC, plus AC. And similarly, 3 and 4 are what are called similar triangles, or rather congruent triangles. One side is D, the other side is B, and likewise here. And each of them have area BD divided by 2. And if I have 2 of them, that means that I need to do this. Opening this up, we have this. So now I have AC plus AD plus BC plus BD minus 2BC minus AC minus BD. This cancels out with this. This cancels out with this. And I have BC minus 2BC, which means that I have minus BC at the end. It is a determinant. So you see, in problem set 1, we had this problem about solving a 2-by-2 system. And in there too, sort of this expression came up purely from the perspective of row operations. But now we see that the same number can be obtained from purely geometric considerations also. Okay? Now this is going to hold in general. I still haven't defined the determinant of an arbitrary matrix, but in 3 dimensions, 4 dimensions, it doesn't matter. Whenever you have a square matrix, there's a determinant defined for it. And you're going to have to, for instance, in 3 dimensions, you can think of the determinant of that matrix as, in three dimensions, the volume of the parallelepiped of, that is the image of the unit cube under A. And in 4 dimensions, you can think of it as the 4-dimensional volume and so on. Okay, so this is supposed to be sort of like an intuition pump. Okay, there is some geometry underneath this. Any questions about this? We had already, yeah.
Is it coincidence or
No.
somebody looked for the determinant? They wanted it to work out this way.
I mean, I think there's something deep going on there. Somehow geometry and algebra is very deeply connected. And there's a whole field that essentially tries to use this connection. It's called algebraic geometry. But then again, some people disagree that it's really geometry. And I would say that it's not a coincidence, but why this algebra and geometry matches somehow seems to be something mysterious ultimately. Yeah. Yeah. I mean, probably one of the primary reasons that humanity started getting interested in linear equations is because they had some sort of like geometric sort of understanding of certain problems, and eventually they realized, oh, they can simplify things and abbreviate things and so on. And eventually, perhaps we forgot that we actually started with geometry or something. Right, so because in order to do this argument, you don't really need to be able to compute things. You can say, oh, I have this whole area, and I'm just like cutting pieces off. And whatever is left is going to be my determinant. You can define determinant that way if you want it, without ever thinking of matrices or anything. Yeah. Okay. Okay. One thing I want to mention, this is very important, is this. If I were to take now two 2x2 matrices and apply them in series, then the determinant would be multiplicative. Okay, this is a very important property. Determinant is multiplicative. This means that the determinant of A times B, for AB squared, of course, equals the product of the determinants. It's a very important property. And the idea behind this, so the heuristic behind this, is this. I start, in this case, with the square matrix, unit square. Then I apply B to it, right? So B takes this square to some other parallelogram. Something like this. And I know that the area of this, signed area of this, is the determinant of B. And of course, I can take this even further using A and go to some other parallelogram. Okay? Now note that this number is not only, this number determinant, is not only the area of this parallelogram, but it's also the how much A scales areas in general. If I were to take 4 boxes, the end result would be some other thing, and the area would be multiplied by determinant. If I had some other type of shape, okay, if I had some other type of shape, something like a blob like this, at the end, it wouldn't be as easy to keep track of how it would look like under my transformation, but still, I would be able to say that whatever the area of this is, its image is going to have the same area times the determinant. Okay? So this is a scaling factor in the context of areas or volumes. So this means that the area from here to there is scaled by a factor of determinant of B, and the area from here to there is scaled by a factor of determinant A. Well, certainly those scales should multiply. Okay? Should we do this calculation? At least in 2 by 2 we can do this. In higher dimensions it's not as straightforward to verify this, but if you want we can write everything out explicitly and see.
I just have a quick question.
Yeah.
Isn't it the rule that your matrix is invertible only if the determinant is not 0?
Uh-huh.
And I guess the reason for that is because if it is 0, then you're collapsing it
Yes.
into the null space.
Yes.
And there's no way
Yes.
for that reason.
Yeah, so think of it like this. We haven't discussed this yet, but it is true that a matrix, a square matrix, is invertible if and only if its determinant is not 0. I guess we did discuss it in 2 by 2. In the 2 by 2 case, this is true in general as well. And the point there is that I'm telling you that determinant of A is the area of this parallelogram. When can the area of this parallelogram be 0? If it is a degenerate parallelogram, if it is collapsed, right? So let's say, so think of that this edge is collinear with this edge, in which case there is no area. The area would be 0, okay? Yeah, it's a good observation. Should we do this calculation in 2 by 2 or no? Maybe I should leave it to you. It's not very illuminating to watch other people do it. Exercise. Verify this. For 2 by 2. Okay. We had already computed a bunch of determinants a couple of weeks ago, I think, for 2 by 2 matrices, so I'm just going to leave it at this. Let's move on to higher dimensions, and let's just first look at the 3-dimensional case. Now, I'm going to give you 2 rules that are essentially the same rule that doesn't quite scale to higher dimensions. Okay? So the rule generalizes this idea. I have these two, okay? When you're going this way, you have a plus, and when you're going this way, you have a minus. Okay, this means that AD is going to be a plus term, and then BC is going to be a minus term. In 3 dimensions, you apply the same reasoning. Determinant of a 3 by 3 matrix. Of 3 by 3 matrices. Let's just focus on examples. For instance, here's an example. Let's look at this matrix. A equals 1, 5, 0, 2, 4, minus 1, 0, minus 2, 0. So I'm going to have beams of light, I guess, or rays going this way and that way. From up, down, this way. So I have this, but I'm going to have also this. This doesn't quite work because clearly I'm not using all of these numbers. I cannot just say 1 times 4 times 0 minus 0 times 4 times 0. That just doesn't use these other numbers. So somehow I need to use them. What you do is this. There's a couple of different ways of doing this. One way of doing it is like so. You take these columns and you duplicate them here. Okay? So you put it, maybe I should not write on the original example. Write this again. 1, 5, 0, and I've forgotten all the other entries. 2, 4, minus 1, 0, minus 2, 0. So we start with this. I want to do this crisscross business. So what you do is, you take these columns, duplicate them here. So 1, 2, 0, 5, 4, minus 2, 0, minus 1, 0. This is the original guy. Now I'm duplicating this here and this here. So now you see, by using diagonals, I get to use every single entry. So this is going to be one diagonal, second diagonal, third diagonal. These are going to be plus. And I'm going to have three diagonals this way, one diagonal, two diagonal, three diagonal. These are going to be minus. So the determinant here is this. This is a plus term. 1 times 4 times 0. Let me write it explicitly just for this time. 5 times minus 1 times 0. That's a plus. Zero times 2 times minus 2. These are the plus terms. Now I have the minus terms. 0 times 4 times 0. One times minus 2. You start with a minus, okay? 1 times minus 1 times minus 2. Maybe I should write it like this. I should have extra parentheses so that this is clear. Minus. Minus. And then I have on final term 5 times 2 times 0. That's going to have a minus. So now one needs to compute this. 0, we're lucky because most of the entries are going to be 0. 0, 0, 0, 0. This is also 0. All I have is this. So this is minus 2. Okay? That's how we compute the determinant of a 3 by 3 matrix. So what does this mean? Forget about the minus first. I have 2 here. This is really telling me that if I were to start with the unit cube, just like I did over there, but in 3 dimensions, apply a to it, it would turn into a parallelepiped, I guess. It's hard to see the edges here. One point is here, the other point is here, the third point is there. If you were to compute the volume of that shape, I'm telling you it would be 2. But then you have a minus here, and that has to do with the fact that A apparently is flipping the orientation in 3-dimensional space. It's flipping the right-hand rule, turning it into the left-hand rule. Okay? I should also mention that after yesterday's class, I came up with a nice way to sort of switch between those two perspectives. Recall that yesterday we discussed how you can think of this picture as a 3-dimensional thing in 2 different ways. The trick, I think, is to decide whether x is coming toward you or going away from you. If x is coming toward you, then you put your right hand like this, okay, toward x. You curl your fingers toward y, and then your thumb points at z. But if x is going away from you, you put your hand like this, okay? And then y is going this way as well. So this should be like this, and then the left hand turns out to be the correct one. Okay, is this kind of okay? How many of you have computed determinants before? Okay. So this is one way of doing this. Here's another example. Let's look at something like this then. They use the same matrix here. I want to use a different one. Okay, let's use this one. 8, 9 minus 6, minus 5, 7, 3, 1, 5, 0. Okay? Okay, let me use the same method again. Another way to do the same thing is to duplicate, instead of columns this way, you can duplicate rows this way. And again, do these 3 arrays this way, 3 arrays that way, and it compute it that way also. But let's stick to the first method that we looked at. Let me also verify that I didn't make a mistake earlier. Yeah. Okay, I duplicated. So now, 1 plus term is 0. Okay, second plus term is 27. Third plus term is 30 times 5 is 150. Now I have minus terms. First minus term is minus 42, so that's a plus. Second minus term is 40 times 3 is 120. Third minus term is 0. So now one needs to compute this. I guess maybe I should write it like this. Now one needs to compute this. These two give me 30. So 27 plus 30 plus 42, which then gives me 27 plus 72, which then gives me 99. Luftballons. You can do it this way, okay? Now, yet another way of doing the same thing is without duplicating these columns or rows, but instead of using arrays, you use possibly triangles. Okay, it's the same idea, but you can do it this way as well. Let me write it over here only. Another way. And let's use this. Of course, this is the determinant of A. Another way to do this is like this. Okay, I'm going to write this 2 times so that it's easy to see. 8, 9, minus 6, minus 5, 7, 3, 1, 5, 0. And I'm going to put these bars just so that I don't confuse it with a matrix. And then I'm going to have a minus term as usual. So this allows you to lump the minus terms all together. 1, 5, 0. So before we use it like we did it like this, okay? These were the pluses. And then I had 1 minus, second minus, third minus. So now the plus, instead, I'm going to draw like this, okay? Then what? Yeah, so this, okay, yeah. Got confused, then, okay. So I just, instead of having this 9, 3, 1 going out of the matrix, I have now a triangle. And then the third triangle looks like this. And then I have the same thing for the negatives. It's going to be the symmetric pattern of this. So you're going to have to reflect this pattern. Okay? And then like so, like so. This would also compute the same number. So you can do it either way. Okay? Now, yet another way, which is somewhat more perhaps exciting, is to use these wire symbols that we discussed yesterday. Now, note that we have 6 terms in the computation of the determinant of a 3 by 3 matrix. And likewise, yesterday we discussed how in 3 by 3 we have 6 permutation matrices and correspondingly 6 wire symbols. So I can do it like this as well. Let me take the same example. 8, 9, 6. Yet another way. So I'm trying to compute the determinant of 8, 9, 6 minus 5, 7, 3.
150.
Oh, thank you. Okay, I know that I'm going to have 6 terms. So I'm going to write the 6 wire symbols that we talked about yesterday. So, and then this, 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 and then I have this, and then I have this. And recall from yesterday, the signs for these corresponded to how many crosses that I had. Or, in other words, whether or not a certain permutation changes the chirality of your space. So based on that, the signs should be like so. It's a plus, minus, 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 plus, plus. Okay? So now, how do I interpret this? I say, oh, I'm looking at the 1, 1 entry, 2, 2 entry, 3, 3 entry, and I'm multiplying them. Okay? Okay, so this is 8, let me write this explicitly, 7, 0, minus. Now I need to look at 1, 2 entry, multiplied by the 2, 1 entry, and then 3, 3 entry. Say 1, 2 entry, 2, 1 entry, 3, 3 entry. Okay? Times minus 5, times 0, and so on. Let me not finish this. I hope you get the idea. So for instance, this corresponds to multiplying 1, 2, which is this, 2, 3, which is this, and then 3, 1, which is this. Okay? Now the interesting thing about this is that those methods don't quite scale to higher dimensions. There is no, let's say, there's a rule, but is any rule that could possibly exist in higher dimensions that is as simple as this, there's no such rule, is what I'm trying to say. There are rules, but they're not as simple as this. It's much harder to keep in mind and so on. On the other hand, this method does scale to higher dimensions. If I had a 4x4 matrix, certainly I could write all wire symbols. So these symbols correspond to 4x4 permutation matrices. And I could keep track of the signatures like this and add everything up. Okay? Of course, then you end up needing to sort of be able to you end up needing to be comfortable with these wire symbols. So there's a much more algorithmic approach, which is much more recursive. And that has to do with this idea that in, for instance, wire symbols, that change 3 different objects, that shuffle 3 different objects, I'm really seeing copies of shuffles of 2 objects. So for instance, this was a 2x2 permutation, if you want, and this too is a 2x2 permutation. So you can descend that way as well. So this is now, so this scales to higher dimensions. Those two don't scale to higher dimensions. And here's a final method that also does scale to higher dimensions, but it is also more explicitly recursive. Yet another way. This is a recursive algorithm. So you start like this. Let me again take the same matrix. You choose any row or any column you want. Okay. Let's just say that I chose the first row. Let me write it like this. It becomes complicated when you write it in words, but let me just do it first, and then perhaps I can describe it later. So our task is to compute this 3 by 3 determinants. And I told you this is recursive, meaning that somehow I need to relate this to determinants of 2 by 2 matrices somehow. The way you do it is like this. You choose a row or a column. Let's say that I chose this row. Now I'm going to sort of go one by one through each of these entries. And based on which entry I choose, I'm going to burn certain parts of the matrix. Okay? So this determinant equals this. I'm going to write it 3 times now. Because I chose this first row, I'm going to pick entries from this first row. Here I choose this first entry. When I choose this first entry, I'm also burning any other entry in the row, in the same row, and in the same column. Imagine sort of like there was this old game called Bomberman or something. There's like a maze, and like you can put like bombs, and like the bomb clears out everything in the same direction. Think of it like this. You put a bomb here, this goes away. This also goes away. Now you have a 2 by 2 matrix. Okay? Here, now you use this one. Again, you get rid of everything in the same row and in the same column. Again, you're left with a 2 by 2 matrix. And finally, you have this. You need to be worried about the signs also. So the top left corner is always positive, and then when you're going from one to the next, you're always switching signs. That is to say, this is a plus, and then now you're using the second entry, so whatever this is, it has to be a minus, and then you have a plus again. Okay? So what does this mean now? What does this burning and everything mean? It means that you're going to take the determinant of this 2 by 2 matrix, which we know how to, I mean, I erase it at this point, but we know how to compute the determinant of this, and then multiply that number by this number. Then I'm going to switch over to this. I'm going to compute the determinant of this 2 by 2 matrix, multiply it by this, and put a minus in front. Then I'm going to go compute the determinant of this 2 by 2 matrix, multiply it by this number, and add it to everything else. Okay, so let's do it. So this is 8 times minus 15 minus 9 times minus 3, and then plus 6 times minus 25 minus 7, 32. Minus 32. Okay? So the claim is that when you do this computation, you get back, again, the same number.
You can use that same method to find the cross product between two vectors.
Yeah. Cross products are related to areas as well, right?
It's negative 6, is it not?
Negative 6? Oh. Yeah, I guess if you, yeah, sure. If this is wrong, then this is also wrong. And here, minus 6. Assuming that the numbers were the same that we started, the numbers that we started with are the same, you should get back the same number in here as well. Any questions about this?
So if you represented like because the wires, if you represented the wires like tetrominoes again, so would I guess if you had like an even number and the row above, would that mean the sign would be positive, and if it was like an odd number, it would be negative?
It is slightly more complicated than that, but for each tower, if it is of even length, then it has to be a minus. But for each tower, you have to do this. So in the case of 3 by 3, we only had one tower of length 2. Let's look at an example for 4 by 4 and display these two cases and how we could do it. So okay, so how does this scale? You use the same idea if you have a 4 by 4 matrix, for instance. If you have a 4 by 4 matrix, you choose any one of the rows or any one of the columns. You start doing this Bomberman trick. You get rid of the corresponding rows and columns. You're left with a bunch of 3 by 3 matrices. Now you have to compute the determinants of those matrices. And in order to do that, you need to get rid of more things again to reduce it to 2 by 2 and so on. Now, this is an arduous process, and you should know it. But eventually, this is not very applicable, really. Especially when it gets to higher dimensions, this is not very applicable. And that is also one of the reasons why I discussed LU decomposition earlier this week. Because recall that in LU decomposition, we're able to start with one matrix, and we're able to factorize it using elementary row operations. So if we can figure out how elementary row operations, which ultimately are just matrix multiplication, change determinants, or in other words, what the determinants of elementary row operations are, then it would be much easier, computationally speaking and perhaps intellectually speaking as well, to compute things. We're going to get to that, but let's do an example for 4 by 4. Well, in the case of 3 by 3, of course, this method still is much better than LU. But if you had at least a 6 by 6 matrix, LU would be better. So let's think of this example. I mean, let me just add a bunch of numbers in that. So say I want to compute the determinant of 8, 9, minus 6, 3, 1, 5, 0. And then let's add a couple numbers. 1, 0, 1, 2, 1, 1, 0. In terms of wire symbols, in 3 dimensions, wire symbols came from permutation matrices. I have 6 permutation matrices, which is 3 factorial. In the case of 4 by 4, I should have 4 factorial many wire symbols, that is to say 24. So first look at the categories, the tetromino types. I have this, okay? I have this. I can have this. I can have this 3, 1, which is the sort of transpose of this if you want. And then I have finally this. Okay? So now, according to what I said, any wire symbol in this category should be a plus. Any wire in this category should be a minus. Any wire in this category should be a plus again. Okay? Here, it's also a plus. Here, it's a minus. Let's try to write a couple of them. I'm running out of time, but this is always the most easy one. It only consists of this wire symbol, because this is telling me, recall that I have 4 boxes, so that means I'm not mixing any of the channels. Here, this is telling me I have 4 wires, so I have 4 channels, I'm mixing only 2 of them. So, 1, 4, 2, 3, 1, 2, 3, 4, 1, 2, 4, 3, and then 1, 2, 3, 4. Like this. It should be correct. 5, 6. 4 choose 2 is 4 times 3 divided by 2, which is 6. So this is the exact number. I'm not missing anything in this category. So now this is rather straightforward. You see, this is mixing 2 channels and then yet 2 channels as well. So I have 2 crosses. So I have here something like this. I have here this. And then I have here this. Okay? Oh, I have time. Yeah, let's keep going. This minus. Let me just leave it here. So here, how can I determine how many different terms should I have here? Well, I have 4 different rows or columns, or channels if you want. So first of all, I need to choose one of them. That one is going to be fixed. So that's 4 choose 1. That's 4. Then I have 3 of them. But this should be something like I have 3 people, and I'm trying to have them sit on a circular table. In how many ways can I have them sit? So that means that you need to have to fix one of them, and the other 2 are permuted. Okay, so I have 3 options. 3 choose 2 is the same thing as 3 choose 1, which is 3. So I'm going to have 12 different terms here. Okay. So let's start. 1, 2, 3, like this. 1, 3, 2. 1, 2, 4, third fixed. 1, 4, 2, third fixed. 1, 2, 4. 1, 3, 4. 1, 4, 3. Maybe I'm overcounting here. 2, 3, 4. 2, 4, 3. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 terms here. 4. Oh yeah, it is correct. Sorry. Exactly, yes. Okay, I chose one channel to fix. That gives me 4 possibilities. And then I have 3 left. I have to fix 1, so I'm left with 2. And there are only 2 ways of setting them. So these are all. And finally, we have here this. And so the way you can think of this as is like this. You have, again, a circular table. You're fixing one of the people, and you have 3 spots. So how many ways can you put 3 people in 3 places? That's 3 factorial. We're going to have 6 terms here. You see, it's good to have this heuristic when you're trying to count things. So 1, 2, 3, 4. 1, 3, 4, 2. 1, 4. 1, 2, 3, 4. 1, 3, 4, 2. Oh, let me do it this way. 1, 2, 4, 3. Okay. 2, 4, 3. 1, 3, 2, 4. 1, we still have time. 1, 3, 2, 4. I have 3 more. 1, 2, 4, 3. 1, 3, 2, 4. 1, 4, 2, 3, 1, 4, 3, 2. 2, 3, 4, 5. And then I have a final one. I'll leave that to you. The point is that I have here 1 plus 6 terms plus 3 terms plus 8 terms plus 6 terms again. That's 12 plus 14, plus 4 plus 8 is 24. I'm missing 2. Doesn't matter. When you write down all of these terms, just like I did over here, and when you multiply the corresponding numbers, you get back the determinant. Okay? Or you can do it like you do over here. You can start with this row, for instance, and start burning the corresponding entries. Okay? This is an arduous process. I'm not saying that this is not an arduous process. On Friday, we're going to learn how to combine row reduction to calculation of determinants, and that will be, I think, much more useful. Okay? Thank you. I'll see you on Friday. Okay, let's start. Good morning. Determinants. We were working on determinants, and today I want to perhaps go through a couple of examples and really discuss this rather more convenient way of computing determinants, and that is to use row reductions to simplify the entries of your matrix and then go through these formulas. Above, just for the sake of completeness, I wrote the definition, the formal definition, so to speak. It turns out that this is useful to come up with, or think about the properties of the determinant. And so here are the 3 cases. So in n equals 1 case, I have a 1 by 1 matrix. That is to say, it's just a number, and its determinant is just this thing. So I have in 1 by 1 only one permutation, and its sign is plus. So, and this is supposed to represent the product of the entries of A corresponding to these permutations. And at the end you get A. In dimension 2, of course, we know that the determinant is AD minus BC. Okay, so this is the plus, this is the minus. And according to the formula, I have A, the identity, and A swap. And so this corresponds to multiplying the 1, 1 entry of A and then the 2, 2 entry of A. That is to say, multiply A and D. The sign of this permutation is plus, so it's plus 1. So you leave it like this. The other one is taking 1 to 2 and 2 to 1, which means that I should be multiplying the 1, 2 entry of A and the 2, 1 entry of A. So B times C, and the sign of this, right, because it changes orientations, is minus. And so it produces the formula for 2 by 2 matrices. In the case of 3 by 3, recall that we had a similar thing. Let me just do it like this. This was one variant. This is 1, so this is a plus, and then this is a plus, and then this is a plus. Okay, so I have 3 terms there. You see AEM here, BFK here, CDL here. And then I have the minus terms going the other way around. This is a minus, this is a minus, this is a minus. Now it's getting harder to see, but CEK is a minus term. BDM is a minus term. And AFL is a minus term. Okay? So this is sort of like a mnemonic device you can use, or you can copy rows or columns to the side and just use arrows like this. either way. And so we said that the most important property of the determinant is this, that the product of two matrices, insofar as they're square, of course, when you take the product and then you try to compute the determinant of this product, that number is the same thing as the product of the two numbers that are the determinants of the separate matrices. Okay? So that's one property. Another property that we hadn't discussed before, but it's still true, is that the determinant of the transpose of a matrix is the same thing as the determinant of A. This is not that straightforward to see, but if you think about these permutation terms, for instance, this permutation, when you transpose it, becomes this permutation. So really, when you take the transpose of a matrix, all these terms are still there. It's just that their orders have switched. Okay? So that's one way to sort of think about why the determinant of A transpose equals to the determinant of A. But these two are what we need, really. So let me do an example to use this recursive definition that we were discussing. So for instance, consider this. This is a 5 by 5 matrix. So it's going to be this matrix. 3 minus 7, 8, 9, minus 6, 0, 2, minus 5, 7, 3, 0, 0, 1, 5, 0, 0, 0, 2, 4, minus 1, 0, 0, 0, minus 2, 0. Okay, now let's try to use this recursive definition. Of course, if I wanted, I could just write down all 5 by 5 permutations and list all these terms like this, but there's going to be, in general, 120 terms. And in this case, we have a bunch of zeros. And really, when I'm trying to do this recursive definition, when I'm trying to use this recursive calculation of the determinant, I really want to use these 0 entries. Okay? So at each step, I get to choose one row or one column. Okay? And I'm going to keep going through that row or column. So in this case, because this first column has the most number of zeros, I might as well start with this. So let's choose this one. Okay, so I'm going to keep computing over here. So determinant of A is equal to this. So what was the rule? So first of all, you have to have pluses and minuses. You always start with a plus at the top left corner. And then every other entry has either a minus or a plus, depending on how far it is. So this is a plus. This is one closer. So this is a minus. This is also a minus. This is a plus, minus, plus. Okay? So first, I choose this entry. I'm going to add all these entries like this. Choose this entry. Get rid of the row and the column of this entry so that you're left with a 4 by 4 matrix. Determinant of A equals 3 times the determinant of that 4 by 4 matrix that I'm left with now. 2 minus 5, 7, 3, 0, 1, 5, 0, 0, 2, 4, minus 1, 0, 0, minus 2, 0. And recall that this was another notation for the determinant. Instead of writing the matrix with parentheses or brackets, you put like bars, and that represents the determinant. Okay, so that's the first term. Then what you do is you switch to this guy. It is 0, but let's first write it out just for this first step. You switch to this guy. It has to have a minus in front of it. And you get rid of all the other entries in the same column and all the other entries in the same row. Again, you're left with a 4 by 4 matrix. So now it's going to be like this. So that's a minus 0 times. So now I have minus 7, 8, 9, minus 6, 0, 1, 5, 0, 0, 2, 4, 1, sorry, minus 1, and then 0, 0, minus 2, 0. I'm writing this out explicitly just so that we understand this method. But of course, in this case, I don't need to really write all this down because it's a 0. I'm going to multiply it by 0. It's going to vanish eventually. And when I write it like this, I mean this is just one number, and this is some other number, which is the determinant of this 4 by 4 matrix. At this stage, I haven't computed it, right? So that's why I'm calling this a recursive method. We're going to sort of go further deeper into each of these matrices once we expand. So then you do this, this, this. So that's a plus 0, and then a 4 by 4 matrix, minus 0, 4 by 4 matrix, or the determinant of a 4 by 4 matrix, plus 0, the determinant of a 4 by 4 matrix. Okay, so given that this third term, this term, is the one that I get by choosing this entry, what number should I put into this matrix? Ultimately, it's not going to matter because we're multiplying it by 0, but still, just so that we understand this method, I'm choosing this entry. And next to it, there's a determinant of a 4 by 4 matrix. Yeah.
It'll be the -7, 8, 9, -6. And
Yeah.
then 2, -5, 7, 3, and the bottom 2 rows.
Right, so you're skipping this, and then you look at these two. Okay? So let me just write this one down also. -6, and then, so I guess this. So -5, 7, 3. Skip the third row, because this entry is coming from this. Then use these two. 0, 2, 4, -1. 0, 0, -2, 0. And I'm not going to write these down. I'm not going to bother writing it down, because they're just going to vanish in this case. Okay? So this is the first step. So the determinant of A is 3 times the determinant of this 4 by 4 submatrix of it. This is what you can call a submatrix. Okay? So now we continue. So equals 3 times. Now again, I can, so I'm going to use this recursive method. So now that I have a 4 by 4 matrix that I'm going to take the determinant of, what I can do is I can choose any row or any column and just apply the same reasoning to reduce it to determinants of certain 3 by 3 submatrices of it. So in this case, again, it seems nice to just choose this column because it has 3 zeros. Just like in this case, in the previous step, we had a bunch of zeros that simplify the calculation. In this case, too, it simplifies the calculation. But for the sake of sort of variety, let's choose this row this time. I can certainly do this. Okay? So now we need to be careful about the signs. You see, according to the original sign convention, the top left is plus, minus, plus. Okay? Oh, I guess in this case it doesn't really matter, but plus, minus, plus, minus, plus. So if I were to look at the signs here, this is a plus, because I started with a plus. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay? But if I were to look at this, it gives you the same thing. Doesn't matter. Okay, so the point I'm trying to make is that when you're going to the next step, again, the top left corner is going to have a plus sign. Plus, minus, plus, minus. So it's a plus, this a minus, this a plus. Now again, I'm going to go through all of these entries and add them up or subtract them depending on the sign. But in this case, again, 3 of these entries are 0. So all I need to worry about is this. So 3 times minus 2 times, minus 2 times. Now when I burn the same row and the same column, I'm left with a 3 by 3 matrix. So this is 2, 0, 0, minus 5, 1, 2, 3, 0, minus 1. So that is to say this is 6 times this determinant. Now at this stage you can start using one of those formulas over there, or you can keep going. Okay, it doesn't matter. Let's say I want to choose, so before going further, is this clear? Is this step clear so far? Okay. So let's say that now I want to choose the second row. Again, I count the signs. Top left corner is always a plus. Minus, plus. Okay? And again, I only have one non-zero entry. You see, when I'm choosing rows or columns, I'm always choosing the row or column that seems to be most convenient. So now I can choose this. This is a plus, so this gives me this. Because I'm choosing this, I'm getting rid of this row and this column. And you see, I'm left with a 2 by 2 matrix. This is 6 times plus 1 times, right? 1 times 2, 3, 0, minus 1. And again, at this stage, like it's clear what the determinant of this is. But just so that it is clear that we can sort of apply the same reasoning until we reach a 1 by 1 matrix, we can keep going, okay? So let me say, for instance, I choose this, column. Okay? Same idea, plus, minus. The only non-zero entry here is 2, so I'm going to pick out the 2. 6 times 2 times. So when I pick 2, I get rid of the row and the column. That gives me minus 1 times minus 1. Of course, this is misleading now, because I'm not saying the absolute value of minus 1. I'm saying the determinant, that is of the 1 by 1 matrix whose entry is minus 1. So this is minus 1. Okay? So the end result is that the determinant of this matrix that we started with is minus 12. Any questions about this? Now, this is an example in the textbook, and if you look at the operations, the order of operations that was done, it's different, but they end up with the same thing. And just so that you're comfortable with this idea, you can just try choosing different rows and different columns at each step. You're always going to end up with the same number. It is mysterious why this happens, but really it's due to the definition. Okay? When you're choosing different rows and different columns, you're really sort of saying, I'm going to write out these terms in different orders. That's what you're doing really, underneath the hood. Okay? Is this clear? This computation of the determinant. Any question? Yeah.
So, like so basically every term in here is just correlates to a wire symbol, basically term.
Yes. Okay. Yes. It is slightly more. It is slightly harder to go from that recursive procedure to this, because when you think about it, I start with the determinant of a 5 by 5 matrix and write it in terms of determinants of 4 by 4 matrices. So somehow 5 by 5 wire symbols can be split, should be split into 4x4 wire symbols. Yeah. So there's this recursivity in this as well. For instance, you see this, which is a 2x2 permutation, here, here, and here, with an extra wire. Okay? It is not as clear how this turns into this, for instance. There's a way to see it, but it's not as straightforward. Certainly for purposes of computation, this recursive method is rather more straightforward than just writing out every single entry at first glance and then like plugging in the values. But this too isn't really that good because it might be the case that your matrix doesn't look this nice. This case, in this situation, we were lucky because there were a bunch of zeros. Typically, so you could have a matrix, most of whose entries are non-zero, in which case it wouldn't really be convenient to choose this particular row over this one. But there's still something you can do, and this is based on this first property. Now, we can do row reduction to increase the number of zeros as entries in our matrix. But we also know that elementary row operations correspond to multiplying by elementary matrices. Okay? So by using this first property up top, if you keep track of what the determinant of each elementary matrix is, things can be simplified a lot further before trying to compute the determinant. So before doing that, let me just mention what the determinants of certain elementary matrices are. Or maybe I should mention it this way. We have three row operations, three types of row operations. The effects of the elementary row operations on the determinant. So we had three types of row operations. Does any of you remember any one of them? What they were called or how I can describe them?
Interchanging two rows.
That's one. We need two more.
Was there like the bottom left triangle one?
Yeah, so you can take, or upper left, upper right, it doesn't matter. You can take any row, right? Take a scalar multiple of it and add it to some other row. So this is, I think, what is called replace in the book. And we have a third one. There's a third row operation. Exactly, scaling. So we can abbreviate it like this. Row I, right, is replaced by row I plus C times row J. That's replaced. Of course, I and J are different entries here. Scale is row I replaced by C times row I. And interchange, I can write as row I replaced by row J and vice versa. So I can use a two-sided arrow. The effect of doing this in terms of determinants is nothing. This doesn't change the determinant. Okay, so this is already very promising. Doesn't change determinant. The effect of this is not as easy, but it's still rather useful. The effect of this is that you multiply the determinant by C. And the effect of this is you multiply determinant by -1. Okay? Now, why is this the case? Well, think of the matrices corresponding to these three operations. To operation 1, the matrix, so to any such operation in the first class, replace class, you have either an upper triangular matrix or a lower triangular matrix with ones on the diagonal. Elementary matrices to 1 corresponds either lower unipotent, unitriangular, let me say, triangular, or upper unitriangular. Okay, so for instance, a typical, a general lower unitriangular matrix looks like this. So this is A, B, C. So let me try to compute the determinant of this. Let's use this recursive definition, okay? So let me first choose the first row. Choose this. It has only one non-zero entry, so I'm going to zero in on this. Burn, burn. Okay? So the determinant of this is the same thing as the determinant of this 2 by 2 matrix. And again, I can choose the first row. Burn the same row, same column. You're left with 1. Okay? So doing a certain row reduction on a matrix, right, like this, using the first operation, corresponds to multiplying the matrix from the left by this, by something like this. Or it's an upper triangular matrix. And you can imagine how the same idea applies there and gives that the determinant of a lower triangular matrix or upper triangular matrix with ones on the diagonal is always 1. Because of that, and because of the first property, because determinant of, let's say, LA equals determinant of determinant of L times determinant of A. So let's say that A is the matrix that you started with, and L is something like this. It's a lower unipotent matrix. And we just computed here that the determinant of L is 1, which means that this determinant is going to be the same thing as the determinant of A. Okay? A matrix that corresponds to an operation in the second row, say second type, is going to be a diagonal matrix that is invertible. By the same type of idea, you can also say that CY using the second operation corresponds to multiplying the determinant by C. So C, the 2 diagonal. And let me be slightly more general. Let me just say take an arbitrary diagonal matrix. If I were to take an arbitrary diagonal matrix, let's say the entries, so I only have entries that are possibly non-zero on the main diagonal. So let's say D1, d2, dot, 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 dn, and everything else is 0. Okay? So here I'm saying that if I'm looking at an entry that is not on the main diagonal, it is 0. Well, what is the determinant of D? Okay, so this is like this, 0, and dn, 0. It's like that. Right, we're trying to compute this determinant. Let's use this recursive definition. Choose the first row, let's say. So that gives me a factor of d1. Get rid of these, get rid of these. So now you're left with d1 times the determinant of this smaller diagonal matrix. I can again choose the first row. That gives me a factor of d2. Get rid of this and that. So now I have an even smaller diagonal matrix. And of course, you can keep going like this, right? You can keep going like this and reduce it to a smaller, to the determinant of a smaller submatrix. And eventually, you're just going to get the product of all these entries. Okay? Does this make sense? Well, in this case, in the case of just taking, scaling one of these rows by a number, corresponds to having ones on the diagonal except for one entry. Well, certainly the product is going to be C then. So let's write it like this. Determinant of, let me say, for instance, let's say that I'm scaling the second row. I have a 3 by 3 system. I'm scaling the second row by C. The corresponding elementary matrix is this. And this A is the matrix that I started with. Okay? By the product rule, right, I can split them like this. Well, I can write it like so. 1, 0, 0, 0, C, 0, 0, 0, 1 times the determinant of A. But based on this calculation over here, this determinant is nothing but C. Okay? And so that is why the second type of operation, elementary row operation, affects the determinant by multiplying it by whatever number you're scaling with. Okay? Third one. Well, third one is really a permutation matrix. Let's look at the case of 2 by 2, for instance. Or we can do 3 by 3. It doesn't really matter. But let's just look at 2 by 2. In 2 by 2, it's straightforward what this should correspond to. Right? I should have a cross in the case of the, so if you're talking about it in terms of wire symbols. Certainly, let me do 3 by 3 instead, actually. So something like this, for instance. Okay? This matrix, so multiplying my original matrix from the left by this matrix corresponds to replacing the first row by the second and the second by the first. Okay? So let's compute the determinants. Well, I can do the standard trickle-down argument, right? It's standard recursive argument. Let me just choose the first row. It doesn't matter. I start with plus. So that means that I should have a minus here. Okay? So And the only entry is the second entry, so I have a minus times the determinant of a 2 by 2 matrix. And that's the matrix that I get by burning the row and the column that I'm choosing the entry from. So burn this, I have the identity matrix. Okay? And of course, the identity matrix has determinant 1, but we can keep going. Let's say that I choose this entry, and I'm left with 1. So that's minus 1. Okay? So, determinant of this is the same thing as 0, 1, 0, 1, 0, 0, 0, 0, 1, determinant times the determinant of A, but we just computed that this has to be minus 1, minus determinant of A.
Wait, why is that negative 1 again? Oh, wait.
Because you start with, so I'm computing this determinant, okay? And the top left entry is always has signature plus, okay? So I need to put a minus here. Yes. That's one way of thinking about it, but somehow it is again mysterious. I just told you that you start with plus on the top left side, but it also relates to, it is underneath all this. This is just like a mnemonic device that allows you to remember things. But if you think about it, this particular transformation changes the chirality of your three-dimensional space. Right? So if I were to look at this, and apply it to a typical three-dimensional vector, what do I get here? I get yxz. So what does this mean? This means that this transformation does the following. If you start with the x vector, right, 1, 0, 0, goes to 0, 1, 0. So now it is this way. 0, 1, 0, which is the y vector, now becomes the x vector. Okay? And the z vector is kept as is. Now, we had discussed how you can view this picture in 3 dimensions in 2 different ways, but let's just imagine that we're interpreting both of them in the same way. So let's say that this and this are both coming towards us, so that we're looking down toward the origin. But note that this is the right-hand orientation, whereas this is the left-hand orientation. So this is changing the orientations here. And so that's why this matrix ultimately should have either a +1 or a -1 as a determinant. Okay. So there's an important geometric reason as to why this should be minus as well, but this plus-minus business just allows you to, do the calculations without worrying too much about this underlying geometry. Okay. Any questions about this? So the strategy is going to be this then. When I have the most useful strategy for computing determinants, and this is how computers compute determinants also, when I see a matrix that I want to compute the determinant of, I do row reduction. I don't really need to keep track of exactly which operations I'm doing, but I do need to keep track of the type of operation that I'm doing. And I need to adjust the determinant accordingly. So now let's bring everything together and do an example. For instance, this. let's look at this. Okay. So I want to compute this determinant, let's say. 3 minus 1 to 5, 0, 5, minus 3 minus 6, minus 6, 7, minus 7, 4, minus 5, minus 8, 0, 9. Now we can go through the motions and do this recursive algorithm and compute it. Or we can try to simplify the matrix by using row operations. Okay, in the book they do something. Let me see. Yeah, for instance, if you just wanted to row reduce this matrix, one of the standard choices is to just take this entry and get rid of this, for instance. Right? I can take the first row, multiply it by 2, and add it to this. If I do that, this matrix changes, but its determinant stays the same based on the first property. I'm taking this, multiplying it by 2, adding it here. Um, 0, 5, minus 3, minus 6. The fourth row is going to stay the same also. And this is 0 now. If I multiply this by 2, right, that is a minus 2, plus 7, minus 5. Plus 5. Multiply this by 2, gives you 4, minus 7, minus 3. Multiply this by 2, that gives you 10, plus 4, there should be minus somewhere. Otherwise it doesn't quite work. Yeah. I forget a minus here. Okay, multiply this by 2, that's minus 10, plus 4, minus 6. Okay, so now for instance, if I wanted, I could take this and subtract it from this. Let's do it. Again, it's the first type of operation, which means that the determinant is going to stay the same. Zero, 5, minus 3, minus 6, 0, 0, 0, 0, minus 5, minus 8, 0, 9. And at this stage, I can safely say that this determinant is going to be 0. Whenever you have a 0 row or 0 column, it's going to be, so the determinant is going to give you 0. Okay? Why is that? Because, okay, so at this stage you can say, okay, now I'm going to use the recursive definition. Let me use this very conveniently zeroed out row. Okay, so I'm going to have 0 times the determinant of a 3 by 3 matrix, minus 0 times blah, blah, plus 0 times something else, minus 0 times something else. So eventually you're going to end up with 0. And certainly you can go through the motions and compute this using whatever algorithm you want, and it's going to always give you 0. But this, you see, if you can see relations between rows and columns, or if you try to just like simplify the matrix by, having more 0 entries at places, eventually you're going to start seeing things. Okay, and that's going to simplify the calculation of a determinant. Does this make sense? Okay. Maybe we can do another example. Let's do another example. Let's do this. Let me take, for instance, this, and this to have a 3 by 3 matrix and see what we can do. Just going to take it over there. So here's another example. Let's say I want to compute this matrix, this determinant. 5 minus 3 minus 6 minus 8, 0, 9. So by this stage, we have many ways of computing this. But let's try to use row operations to simplify this, first of all. I can indeed go all the way to row reducing this and getting the reduced echelon form. So what I can do is, for instance, I can take, let's say, the first row, multiply it by 5, and add it to this. Okay? So that's minus 1, 2, minus 5. That's not going to change the determinant. Okay? So this is 0 now, right? 5, so minus 5. Now it's 10, so that's a 7. Minus 25, minus 6, minus 31. And I can keep going if I want it. But you see, at this stage, I really don't want to sort of get rid of this, because if I get rid of this, this is going to be a non-zero entry. So it's not really helping that much when it comes to calculating determinants. I can leave it like this. So I look around. I say, for instance, one thing I thought was, oh, maybe I can scale the second row by 7, or 1 over 7. Let's do it. It's not really very convenient here because this is a prime number. This is going to be a rational number now, and I don't like rational numbers that much, but still, we can do it if I want it, if you want it. Or what I can do is, I can scale the first row by minus 1, because let's say that I don't want to see this minus here. Okay? So scaling corresponds to multiplying. So minus 1, minus 2, 5. 0, 7, minus 31. And let me do this. Let me scale this by minus 1 as well so that I have a plus 8 here. But if I do one more, that's a plus now. 8, 0, minus 9. Okay? So here I use the second operation 2 times. If you want, in terms of matrix multiplication, going from here to there corresponds to multiplying from the left by the diagonal matrix with entries minus 1, 1, minus 1 on the diagonals. And the determinant of this is going to be plus 1 because the product is going to be plus 1. So that's that. I'm trying to see if there are any more things I can get rid of. It doesn't seem like it. So at this stage, what I can do is I can get rid of this. I can simplify this column if I want it. But I can just leave it like this. It's not really that big of a deal. So let's use the first column, 1, 0, 8. Okay, so that's a plus, minus, plus. This means that I'm going to have 1 times the determinant of a 2 by 2 matrix plus 8 times the determinant of some other 2 by 2 matrix. And what are these? If I burn this and that, I'm left with 7 minus 31, 0 minus 9. And if I burn this, I'm left with these. Minus 2, 5, 7, minus 31. Okay, you see this is somewhat ugly, but at least this is rather more straightforward to compute. In this case, this is just going to give me minus 63, because that's minus 9 times 7 plus 8 times this number. So this is 62 minus 35. Okay, let me not finish this calculation. It gives you the number. Ultimately, we reduced this task of computing the determinant to number addition and subtraction. Okay? Any questions about anything? So this is all there is to it when it comes to determinants, at least for now. Of course, as we continue in this class, we're going to learn how to use determinants in more and more sophisticated and higher level contexts. But for now, I think this is all you need to know. Okay? So row reduce and keep track of how the determinant changes. And eventually, once you've simplified enough your matrix, start using the recursive formula. Okay? I think that's it for this week. I'll see you next week. Thank you.